This video is going to look at Riemann sums and sigma notation. So how we can use sigma notation to represent Riemann sums. So Riemann sums, as we talked about before, Riemann sums are the standard way to calculate the area under the curve. So the standard way to calculate the area under the curve. And we write this as the sum from I equals 1 to some number, depending on how many rectangles we want to use, of f of xi times delta xi. So in other words, as we go through, we're going to take the height of some rectangle and multiply by the width, or that delta x of some rectangle. And delta x, or xi, and be any value on that range. And I think we'll actually talk about this in a minute here. But we're just multiplying a height times a width. So the more rectangles used, the better the approximation, right? If you use 100 rectangles, it's going to be better than using 2. And you probably saw this in your exploration, and so you have kind of an idea of it. This f of xi can be the value at any point in the partition or in the interval. So it can be the left side, it can be the right side, it can be the midpoint, it can be the trapezoid. And that's because we don't really care about distinguishing what kind of Riemann sum we're doing here. But with infinite partitions, the sum will be exactly equal to the area under the curve. And this is why we don't particularly care about what x value you choose, because as those rectangles get thinner and thinner and thinner, the left and right endpoint, or the left and right values of the function get closer and closer. And if you get an infinite number, they become infinitely thin, and any point that you pick will be identical. So we have this note here that dx is a differential, which is an infinitely thin interval of x. And so what we end up having is we end up writing something like this. The sum from 1 to infinity of f of xi delta xi is equal to the interval of f of xi times dx. Because this dx, as delta gets smaller and smaller and smaller and smaller and smaller, when you get to the smallest number that isn't 0, that's your delta x, essentially. And these will be infinitely thin rectangles here. So that leads us to the idea of, with Riemann sums, we can talk about 2 types of integrals. Definite integrals can calculate the total accumulation of change of a function over a specific domain. So this is a total over a specified domain, and that will end up looking like this. The integral from a to b of f of x dx is equal to what we just saw before, I equals 1 to infinity of f of x I delta, dx. So the infinite Riemann sum is, by definition, this integral. When the antiderivative, and again, this is some language that we'll worry about later, don't worry about it for now. When the antiderivative is known for a function f of x, that function can be integrated, and this is known as a indefinite integral. And it looks something like this. And you'll notice that these are kind of like evaluating the derivative at a point versus evaluating the derivative as a function. So the definite integral gives you an area. It gives you a number as a result. And so that's like finding the derivative at a point. You can get an exact number, you get the slope at that point. The definite integral gives you the area between 2 points on a curve. The indefinite integral is like calculating the derivative function. It gives you a function that tells you how much accumulation, how much change have we accumulated so far. So then you can come along and plug in values for x to say between 0 and this point, how much change have we accumulated? Between 0 and this other point, what change have we accumulated? So these two types of integrals, we'll spend a lot more time distinguishing them, talking about them, but I want to introduce this language and just tell you to think about it's like finding the derivative at a point versus finding the derivative function. One tells you specific, detailed problem, the other tells you the general solution.